We can start with this session on routing. And we have 3 papers, and as Emmanuel has mentioned, the query and answer session will be postponed later, so we will have the presentation currently, and afterwards we will discuss about the papers themselves, merging both the routing sessions. So the first paper will be a paper by Nicolas Isoart and Jean-Charles Régin, and it's about CP-based Lagrangian relaxation for TSP. I don't know whether we have a registration. Yes, we have a registration. So let's have a look at the presentation.
Hello everyone, I'm Nicolas Isoart and I will talk about the work done with Jean-Charles Régin on the adaptative CP-based Lagrangian relaxation for the TSP solving. This work was done at the I3S, a French laboratory in the University Côte d'Azur. The traveling salesman problem is the NP hard or NP complete. It depends on the variance. It has for data a list of cities and the distance between each pair of cities. This problem is constrained with 2 constraints. The first is to visit each city only once. The second is to find the shortest cycle. The TSP is a fundamental problem in computer science motivated by many applications in the industries. Here on the left, we can see the map of the USA and the solution of the TSP going through each red cities by blue edges. Now, I'll give you a short introduction to the filtering algorithms of the weighted circuit constraints. That is a constraint used for modeling the TSP in CP. Take a graph, like the left one on the slide. Make the hypothesis that we know the length k of a Hamiltonian cycle in the graph. So k is an upper bound for the TSP. Now, with some algorithms that I will not explain here, we can remove edges preventing the existence of a Hamiltonian cycle lower or equal than k and identify mandatory edges for the existence of a Hamiltonian cycle lower or equal than k. It allows us to take the left graph, apply this process with those filtering algorithms, and obtain the right graph. Thus, the search space will be considerably shrinked. In practice, it is easy to obtain such a K, for example with some heuristics for the TSP, like LKH, that are very fast. The Lagrangian relaxation procedure uses the idea of relaxing some difficult constraints by bringing them into the objective function with associating Lagrangian multipliers mu greater or equal than 0. On this slide, assume that the constraint a1 times x lower or equal to b1 is difficult to solve, whereas the constraint a2 times x lower or equal to b2 is easy. Then, the Lagrangian relaxation moves the end constraint into the objective function and associates a Lagrangian multiplier mu to this constraint. We can define d, the distance to the satisfaction of this constraint. Intuitively, by using mu, the larger d is, the more the constraint should be penalized, and the smaller d is, the less the constraint should be penalized. Finally, the Lagrangian multiplier problem proposes to use a non-negative multiplier for each constraint introduced into the objective function and to find the best set of multipliers. The property 1 saying that for any vector mu, the value of CL or mu is the lower bound of C is really important, because as I said, we need a lower bound to perform the filtering algorithms. Thus, the combination of filtering algorithms and the Lagrangian relaxation is valid. Since filtering can be done with suboptimal multipliers, the subgradient algorithm is suitable. Subgradient algorithms work in steps and reoptimize locally the multipliers according to a certain precision called agility. It contains 2 nested loops. The first one is based on the number of times the agility precision is narrowed. The second one is based on the scope, that is the number of times the optimal value of the Lagrangian relaxation is computed and multipliers are updated. During the optimization phase, it calls function solveLR, which computes the optimal value of the Lagrangian relaxation for a given set of multipliers and defines the new multipliers. It is also useful in practice to have the function stopCondition, which takes some parameters and tests if some stopping conditions of the current loop are met. In CP, the filtering can be either in the scope loop or just after the loop. If the filtering is performed in the loop, then the filtering may be called too often and become time-consuming. Perform the filtering outside the loop may have the opposite effect. So, it becomes essential to determine when to perform the filtering step. To understand this difficulty, Salesman made two important observations about the relationship between the Lagrangian relaxation and the filtering algorithms. Suboptimal multipliers can link to a stronger filtering than optimal multipliers, and the filtering can disrupt the search for improving multipliers. Now, I will introduce the idea of subgradient scope size algorithm. In the top graph, we can see the evolution of the objective value during an optimization step. There is 6 iterations over the agility value with a scope equal to 30. An agility iteration is displayed by going from a green square to a black square. SSSA ID is to cut the optimization step, that is break the iteration over scope, if one of the following pathological cases arise. First, a strong variation followed by oscillations. Second, a weak variation followed by oscillation. Then, almost no variation. If we implement our proposal, then we get as a result the bottom graph that we made coincide with the top graphic to show the difference. We can see that the difference between the two objective values is very small compared to the number of avoided calculations. So, for SSSA, we propose the following modifications to the Bisley algorithm. First, we define the agility from 1 to 6. This has been defined empirically. Second, we define the scope from 2 to 12. We have empirically determined that after 12 optimization phase, the trade of optimization versus filtering was on average no longer very good. Then the optimization is repeated by a block of 2 while observing the variation of the objective value. This variation is kept in the mean variable. For the stop condition, we define with respect to the two previous steps. If there is a variation of less than 1% with respect to the difference between the upper bound and the lower bound, then we stop. It allows us to deal with in practice with the case of oscillations and non-position periods. So, there is at least 2 optimization rounds and at most 12. This makes the algorithm adaptive and prevents us to inferring values on the number of optimization steps to perform. Now we are going to look experimentally at the scope value. Each column of this table gives the average resolution time and the number of backtracks for a given search strategy. If we take a small scope, 2 for example, we notice that for each search strategy, the average resolution time and the number of backtracks tend to be higher than the result obtained with a larger scope. It means that a lot of filtering and very few optimization steps is not a good idea, because there is not any difference between the different lower bounds used for the filtering step. If we take a larger scope, we refine the lower bound and therefore we expect the filtering to be stronger. It is not true for every case. For example, with mean delta deg, we notice that scope equal 12 takes 74.4 seconds, while scope equal 6 takes 33.9 seconds. Since the growth of the lower bound is not monotonous, setting a priori scope is not a good idea. It can link to a filtering being triggered while the lower bound is not improved or even degraded. The time spent for the optimization is finally lost. Finally, we notice that for each search strategy, the best average scope value changes. 8 for LC first max cost, 6 for LC first min up cost, and LC first min delta deg. In fact, we notice that beyond scope equal 12, it is extremely unlikely that the trade-off is good. For the record, we tried to raise the scope up to 1000 and time are really bad. Thus, we define empirically that a good scope value for the solving of the TSP must be between 2 and 12. Now, we will set the search strategy and look for each instances which are the best and the worst scope values. We notice that for a given instance, the best scope value changes very often. We have 12 for A280, 8 for CH130, 4 for group B100. Thus, it is not enough to set a scope to the same value for the resolution of all instances. The scope must be adapted to the instance. We also notice that a very small scope is often a very bad idea. If we knew before the solving of an instance the best possible scope value for its solving, we would gain the factors described in the ratio column compared to the worst scope value, that is a factor of 2 or even 3. But there is an issue to know the best scope before solving an instance. You have to solve the instance with all the scope value you consider, and therefore you have solved the instance several times. So, to avoid this test phase, we propose to use SSSA, which does not make any a priori on the scope value, except that is between 2 and 12, and which can make the scope value adapted for each optimization round. For each of the search strategies previously presented, we note the best average scope, the best scope set a priori, and the result obtained by SSSA. A larger set of instances is available in the paper. The average solving times are given in relation to the full set of instances. We notice that SSSA is competitive with the best scope per instance. For example, for LC first min web cost, we notice that choosing the best scope per instance gives an average time of 28 seconds on the full set, and SSSA gives 29.1 seconds, which is very close without meaning any a priori. We can even notice that sometimes some instances are solved faster with SSSA than with the best scope a priori. For example, Corby 150 with the LC first min web cost strategy is solved in 358.6 seconds with the best average scope, 291.4 seconds for the best scope for this instance, and 238.3 seconds with SSSA. Finally, we compare FLR, which is the best configuration of the Lagrangian relaxation used until now by Fudge and al. In Choco with SSSA. We notice that about a factor 2 our resolution time is obtained regardless the search strategy used. Then, the use of SSSA has a strong practical interest. To conclude, the goal of this paper was to improve in practice the use of Lagrangian relaxation in CP. A first step was to determine when the filtering algorithms should be triggered. Our study allowed a better understanding of the problem and to obtain robust results. The use of SSSA allows for each instance to avoid losing a factor of 2 or 3 if the scope is set to a wrong value, and makes the use of SSSA interesting and powerful in practice because it makes the use of Lagrangian relaxation in CP more flexible. To continue this work, we will try to integrate and generalize SSSA to solve other problems using Lagrangian relaxation in CP. Thank you.
So thanks for this nice presentation. We have a very short question besides those that can be made during the official query and answer session. That is Raphael Boudreau that is asking what are the instances used in these experiments, whether they are coming from TSP lib.
Do you hear me?
Yeah.
Indeed, the instances are from the TSP lib. It's wrote in the paper, and I forget to tell this during the talk.
Okay, so apparently we are perfectly on time, and if there are no other short questions, are there?
There is no more question.
Okay, I have a short one. It seems indeed that the range for scope is from 2 to 12. do you have any evidence what's happening with much higher values for the scope? So it's useless actually to use them, or it's worth investing also higher values?
For the record, we tried up to 1000, and we said that after 12, the optimization phase is much longer than the result we obtain with filtering more. In fact, the optimization phase tend to stagnate, like the Plateus I showed in the figure. So the short optimization phase, but not too short because the lower bound are bad, is good. So between 12 and 10, the selection is not straightforward. That's why SSSA is a good candidate with no a priori for the scope choosing.
There is another question by Kevin Dalmeyer, who is not familiar with CP-based methods, but how the performances compare with respect to MIP solutions?
For the whole solving of the TSP, there is Concord with the MIP, but it cannot handle all the instances. That's why we investigate for the TSP resolution method, because adding constraints in the CP model is really easy, because in CP adding constraints it's easy, and in Concord, if we add some constraints, the resolution of the problem can be very slow, very bad. So that's why CP is good. So there is MIP with Concord. There is the constraint and the model I present for CP, and there is other LP formulation and heuristics.
Okay, we still have time for one other short question, and the next one is again by Raphael Boudreau, and he's asking on what extent you can extend your work to other problems or to other using this kind of CP-based Lagrangian relaxation.
Because my thesis is focusing on the TSP, I guess we firstly try during the time I have for me, I will be extend the TSP for the TSP TWE because I guess it's a good idea. And maybe we have to investigate which problem are using and working with Lagrangian relaxation, and maybe the set covering is the next good candidate for our research.
Okay, so thanks again for the presentation, for the answers. So a virtual applause. So we can proceed with the next talk, which is about heuristic search, in particular guided performance learning to the applied to traveling salesman problem.
Good afternoon. My name is Benjamin Hogstad. I'm here to present our work on a search heuristic guided reinforcement learning approach to the traveling salesman problem. The TSP is an NP-hard combinatorial optimization problem consisting of finding an optimal sequence of nodes given a set of them. There's been a lot of work developing search heuristics to find solutions to the TSP which result in good but not optimal results. Exact solvers are available but generally require extensive computation time to find a single solution. Deep learning offers an approximation method which can speed up inference at the cost of extensive training time. Reinforcement learning has resulted in promising results as seen in Thorsten and Kuhl, and interestingly, Thorsten combined a search heuristic with reinforcement learning. We propose an approach which expands on this idea. We chose 3 heuristics. Nearest neighbor, which chooses the next node based on the distance between the remaining nodes, choosing the shortest distance. Sweep, which chooses nodes sequentially based on the order of their angle. And finally, the 2-opt heuristic, which, unlike the 2 previous, is not sequentially construct a tour, but instead takes a tour and improves it, doing so by swapping 2 nodes and evaluating if that improves the result. These heuristics were chosen due to their simplicity and uniqueness in their solutions. Each search heuristic provides guidance to the model at each time step during training. Note that the actions are always aligned, and these guided actions are inputted into separate loss functions and then compiled into the normal reinforced loss, gently pushing the model towards their own actions. An inflation study on the 20-node TSP showed that providing the model with guidance in various forms improves results. Each heuristic individually improved the baseline as well as combining all three. The model quickly outperforms the construction heuristics, so increasing their usefulness or decreasing their detriment was of concern. To increase their usefulness, the heuristics filter out k nodes and allow the model to choose the respective guided action based on its own assigned policy for these filtered nodes. To decrease their detriment, alterations of the penalty factor utilized in the combined loss function were also assessed. The best result was by linearly increasing the filter parameter k throughout the run. This resulted in improving the optimality gap from 1.0573 to 1.0500 using Doiden's model and 1.0407 to 1.0335 in Kuhl's model. When run on 50 and 100 nodes, the results are more mixed. The heuristic guides generally provide improvement over the baseline in all but the 100 nodes using the Kuhl model. Note that there is a slight increase in training time due to the use of these heuristics. The guided approach increases runtime by approximately 1.7%, and the linearly increased K resulted in an almost 7% increase. Further work can be done on utilizing better performing heuristics, and thank you very much for your time and enjoy the rest of the conference.
So thanks to the speaker. Are there any questions? Any short question? We have time for just one. Quick. If not, so maybe we can proceed with the next talk and then gather all the question in the next query and answer session later. So the next talk is about the minimum cycle partition with length requirement, and I kindly ask to start with the presentation.
Ja, grüß Gott nach Wien und in die Welt. Hi there, greetings from Berlin. My name is Kai Hoppmann, and today I present you our work on the minimum cycle partitioning problem with length requirements. This is joint work with my former student Johnny Mexi and my advisor Thorsten Koch and our colleagues and friends from Linköping University, Oleg Burdakov and Johan Casselgren.
Yeah, before we come to a mathematical model for the minimum cycle partition problem with length requirements, first of all I want to show you one of the applications where it is useful, and this is the routing of agricultural UAVs. UAV stands for Unmanned Aerial Vehicle here, and so these agricultural UAVs are commonly used in the US, and so these are like drones that are equipped with sensors and or like cameras and can make images, and they gather important information for the farmers. So information such as irrigation problems, if there are pest and fungal infestations, or if there is a soil variation. And yeah, of course, if you have all this information at hand, the farmer can optimize his or her agricultural operations, such as to increase maybe the water frequency for some fields, or yeah, to fight against a fungus which the field may be impacted by. So the problems we have here, we have a set of areas to monitor, which we denote by V, and for each area we are given a scanning time, which is the time that the UAV needs to scan this field or area. And most importantly, we are given a critical weight, and this is the maximum time between 2 consecutive scans. So just imagine you have different fields, and one of the crops is very valuable, so you may want to visit this more often with your UAV in order to check if everything's okay than the other fields, so the critical weight would be lower in this case. Of course, we're given the flying time between the different areas. So here come now the restrictions. So we want that each area is monitored by exactly 1 UAV, so only 1 UAV is assigned to each area. If you want that the UAV fly cyclic tours, that means that they start their tour, visit their assigned areas once, and end with its tour at the point of origin. And yeah, as I said with the critical weight, so we say now that the length of the tour is not allowed to be longer than the minimum critical weight of its vertices. So imagine there's a field where you have a critical weight of, let's say, 30 minutes, then the whole tour that the UAV needs to go to the fields and scan them that are assigned to it is not allowed to be longer than these 30 minutes. Now let's give a mathematical formulation of CPLR, so the minimum cycle partitioning problem with length requirements. We are given a complete undirected graph together with edge weights for each edge. It's important to note that the edge weights satisfy the triangle inequality here. We are giving the critical times for each vertex and the scanning time for each vertex. Down here you can see an example graph with the edge weights in black, critical times in blue, and scanning times in red. So what we are looking for is a feasible solution. A feasible solution is a cycle partition, such that for each cycle its length is smaller than or equal than the minimum critical time of the vertices that are contained in it. So we also say a cycle is feasible if it fulfills this condition. The length of a cycle is given as the sum of its edge weights together with the sum of the scanning times of the vertices that are contained in it. And the goal of the problem is to find a solution that minimizes the number of needed cycles. And here we have an example solution. So a singleton, or like a single vertex, is always a feasible cycle. So we have also always have a trivial solution, which is just assign each vertex to its own cycle. That's what we call a trivial solution in the following. Here we have a non-trivial solution because we have one cycle here. The length of the edge weights here is 4, while the sum of the scanning times here is 5, and so we have a total length of 9, and all the critical times of the vertices here is 10. So this is a feasible cycle, and we have a feasible solution here in the end, which is even optimal. What you can do now to simplify the problem description is to put the scanning times on the edge weights. So we redefine the edge weights. We say the edge weight is now the original edge weight plus half the scanning time of vertex I and half the scanning time of vertex J. And then this would look like this. So we have now assigned the scanning times to the edge weights, and still, as you can see, the cycle on the right hand side has length 9, and it's still a feasible solution. And it's also important to note that if you do this, still the triangle inequality holds for the edge weights. Well, some of you might now say, well, this has a somehow TSP-ish flavor, like looking for a tour of short length. And yes, there is a relation to TSP, and this becomes obvious when you look at the complexity proof. So CPLR is an NP-hard problem. You can. This is easy to see. So you take an instance of the TSP and consider just some value big B. And now, if you assign each vertex of the TSP instance and B as its critical weight, you derive an instance of CPLR. And you know that the optimal solution of a CPLR instance consists of exactly one cycle, if and only if there is a Hamiltonian cycle with length smaller than or equal to B in the underlying graph. Well, now we want to talk a little bit about preprocessing. And so the first thing that becomes obvious is, so the following theorem: there exists a feasible cycle that contains two nodes, Vi and Vj, if and only if the length of the arc that connects these two nodes is smaller than or equal to the minimum critical weight of these two vertices. The proof is, it's easy to see. This just comes from the triangular quantities. So any path between them which doesn't use this edge is at least as long as Lij, and yeah. So let's denote in the following this set of arcs which are longer than the greater than the minimum critical time of these two vertices. And what we define now is a conflict graph. And we say that GC is the set V and the edge set EC. So this is the conflict graph. So there is an edge between two vertices in this conflict graph if they cannot be contained in a common cycle. And so this already directly gives rise to the following lemma. If we have a clique in this graph, of course, in each feasible cycle in a solution, there can be at most one vertex of this clique, because otherwise, if you have two, there is an edge between them, and as I said, there cannot be a cycle containing these two vertices. Furthermore, we can say if we have a maximum clique in there, this gives us a lower bound on the size of an optimal solution, right? So keep this lemma in mind. The lemma in mind, because later for our mathematical program, our mixed integer programming formulation, we will derive some valid inequalities through it. So next we want to present you the mixed integer programming formulation that we developed for CPLR. We have, first of all, three kinds of binary variables. UK is a binary variable which is equal to 1 if the cycle with index k is used, so if vertices are assigned to it, 0 otherwise. Yi is equal to 1 if the corresponding vertex is a singleton and not contained in a proper cycle having two vertices or more in it. And Zik is equal to 1 if vertex I is assigned to the cycle with index k and 0 otherwise. And from there we already derived like two constraints. So the first constraint here is that each vertex is either singleton or contained in a proper cycle, which is guaranteed by the first constraint. And if vertex I is assigned to the cycle with index k, then the binary variable uk has to be equal to 1. And from that we can already write down our objective function, which is the sum of all singletons plus the sum of all active cycles that contain any some vertex. So for our model now, we consider the induced directed graph. So for each edge we replace by two anti-parallel arcs, which both have the same length as the corresponding edge. And if we do that, we derive the following next constraints. So we first of all introduce new binary variables xi, j, k, which says that arc ij is contained in cycle k if it's equal to 1 and 0 otherwise. And if vertex I is contained in some proper cycle k, so a cycle which has two or more vertices, then there has to be an outgoing arc and an ingoing arc for this cycle. Furthermore, what we can do now, if we now assign these arcs to the cycles, we can determine the length of a cycle, which is then given as the here denoted by the variable tau k. And finally, we have the critical weight condition here. So if a vertex I is assigned to cycle k, then the length of the corresponding cycle, so tau k, has to be smaller than or equal to the critical weight ti of this vertex. So similar to TSP, what can still happen in the corresponding solution, if we only use the constraints that we introduced so far, is that we have subtours in a cycle ck. And to avoid this, we adapted the Miller-Tucker-Zemlin constraints from TSP. So what we do now is, for each of the cycle, we choose a starting node, which is indicated by the binary variable sik. And we say that each cycle that is used, so if uk is equal to 1, there has to be a starting node for this cycle. And now the Miller-Tucker-Zemlin constraints read as follows. So for each vertex we define a weight, and then the constraints on the bottom, they ensure that if you assign a starting node to a cycle, then and if you go from there in the direction of the arcs, then the weights have to increase all the time except for the last step, so from the last to the starting node. And by doing that, you ensure that there's exactly one cycle and that there are no subtours. So finally, we conducted some computation experiments, and our algorithm is the following. First of all, we remove all edges from G that cannot be contained in a cycle, so the set EC. Then we use the result of a cheapest insertion heuristic that we developed for our problem as incumbent solution, and this also gives us an upper bound on the number of cycles that are necessary. So this also decreases the size of our MIP formulation. We generate the constraints with respect to maximum cliques, and these maximum cliques we determine all of them in the conflict graph, and we introduce the corresponding constraints. We add some symmetry breaking constraints in order that only one permutation for each solution is feasible, and then we solve the resulting model. And here is our setup. So we take the TSP lib instances with 50 nodes. From there, so to get the critical weights, we sample between tau star over 6 to tau star over 2, where tau star is the length of the optimal TSP tour. We use Gorobi 9 as a MIP solver. There are the technical details, and we put on a time limit of 24 hours. Now, when we look at the results, we can see that, CPLR actually seems to be a hard problem, at least for the model that we are considering. So we were able to solve the instances with up to 29 nodes here, and you can see that the running time somehow decreases in a sense exponentially with the nodes here, and you can see that the heuristic delivers good results. And also the maximum clique that we find, the lower bound, is also very good, but still it's hard for Gorobi to determine optimal solution in that case.
Yeah, now it's the time to ask questions. Thanks for listening. Unfortunately, we cannot be together in Vienna this year, but I hope this will change in the near future. Ich würde mir freuen. Macht es gut.
Okay, so thanks also to the presenter for this last presentation. There is time for a very short question, so we are running really out of time, and is by Kevin Dalmeyer. Is asking whether have you considered a formulation where the variables correspond to feasible cycles, and in that case, column generation may work well?
Yes, so we have considered this. So actually my student is working on such a formulation. The other thing we have tried so far, so what we've done now recently, is to develop a formulation which is not based on the Miller-Tucker-Semlin constraints, but more on the subtour elimination constraints. We have to adapt them in a similar fashion as for the Miller-Tucker-Semlin constraints, but this works a lot, or not a lot, but this works definitely better than our formulation shown here so far.
Okay, so thanks again. We are almost overlapping to the next session, so we have very few minutes for switching to the next session. So virtual applause to all the speakers. Thanks, and enjoy the remaining time of the conference. I recall that the question and answer session will start at 10 to 6 later. See you.